Welcome to this week's video, and for this week I would like to do something that's a bit different, and I'm going to be starting a new series of videos which are going to be focusing on data structures and algorithms. These are a field that I wanted to improve myself, improve my logic as a programmer, and I thought it would be interesting to go through LeetCode problems and solve them with you, and so we can also discuss the solution here and actually try to improve together as programmers, right? So this platform has over 3,000 problems, right? And I just gonna literally start with problem number 1, and that's gonna be this one called toSum. It has a easy tag, and let's start with the problem. So here it says we have an array of integers called nums and an integer called target, and it wants us to return the indices of the two numbers, which when they are added up, they sum up to the target, right? So for example, here we have the list 2, 7, 11, 15. We see here that 2 and 7 add up to a target, which is 9. And so we want to return the indices of these two numbers, which are index number 0 and index number 1, for example, right? And we're assured that there's only going to be one solution, so there won't be multiple pairs that add up to that target. And the same element cannot be used twice, so we cannot use the same number to add up to that target, right? As another example here, we have list 3, 2, and 4. We have here 4 and 2, which add up to 6, and we then return 1 and 2 because 1 is the index of 2 and 2 is the index of 4, right? And so there's many ways you can solve this, and I think it's interesting to start with the worst possible way, which is to brute force your solution, right? So brute force way would be for you to go and see all of the possible pairs that you can form and then check to see if they add up to the target. That's going to give you a complexity of O of n squared, a time complexity of n squared, which means that for any input of size n that you give, the time that it takes for your algorithm to complete is going to be proportional to the squared of that size, right? So if I double the input that I'm giving, the time that it's going to take to complete is going to grow 4 times as much. If I multiply the input by 4, then the time is going to be increased by a 16 factor, right? So that's the worst possible solution, but let's start with that one just so we can learn together how these things work, right? So we're going to be looping through this list, right, that we get as an input. And then for every single number of the list, we're going to be looping over the list again. And we're going to be checking for every single possible pair. And if we find a solution, we're going to return it, right? So it's simply looping through the structure. So for I in range length of nums, that's going to be looping through our list once. And then for every one of those numbers, we want to loop through that list once again. So for j in range, and here we can do once again length of numbers, right? And then that's going to give us every single pair of our list, and we simply need to check here that if nums I plus nums j, if they add up to the target. And here there's another caveat, because we're looping through that list 2 times for every single number, we're going to eventually reach a point where I equals to j, right? So we're going to be going through the same number twice. And here in the description of the problem, it says that we may not use the same element twice. So we just got to make sure here that I is different than j. So we're not using the same number to reach that target, right? So if they add up to the target and they're not the same number, then we want to return, and they want a list with the indices, right? So it's going to be simply I and j. So we can submit this and see how it works. And you see here the solution was accepted, but it was a very bad solution in terms of time. We only beat 5% of the submitted solutions, and here we have we beat 80% of the solutions in terms of memory. And that's because here we have a constant space complexity because we're only using I and j here. independent of the size of our input, right? So doesn't matter how big we give as an input, we're only gonna need 2 variables, and that's why our space complexity is very good, but our time complexity is very bad. Right away, one of the things that we can do here to improve this is to realize that for the second time we're iterating over this loop, we don't actually have to check things that come before I, because everything that comes before the I has already been checked when I was that number already, right? And so, for example, here we only need to start j starting from I plus 1. So for every element of the list, I'm just interested to see the pairs that are formed after, right? Because the ones that I've seen before were already accounted for. And so here, because j won't now ever be the same as I, we don't need this anymore, because we're sure that I won't be equal to j. But that's pretty much the same, right? So we can try to submit this, see if it works. And you see here it was accepted, it was a bit better. We now beat 18% of the submissions. And that's because now we don't have to loop over the elements that came before that I, because that was already counted for. For the second time we're looping through that list, we're only looking at stuff that comes after the current element that we're in. All right, now that we have seen the O of n squared solutions, let's look into a much better solution which runs in O of n time complexity, which means that for an input of size n, my time that it takes to complete this function is going to be proportional to that n. So if I double the size of my input, it's going to take me twice as much to complete it, right? So that's a much faster algorithm. And for that, the realization we need to do here is to see that we can calculate a special number, which is called the complement, which is going to be equal to the target minus a certain number here in our list. So for example, for number 2 here, the complement is going to be equal to target minus 2. So 9 minus 2 is 7. And we know that 7 is a number that we need to find in that list to find the solution. So if there's a 7 in that list, we know that 2 and 7 are going to add up to that target 9, right? So we're going to be looping through that list once. So that's why it's O of n, because we're only looping on it once. And for every one of those numbers, we're going to be storing that number on a hash map or a dictionary in Python. And we're also going to be checking to see if a complement already exists in the map. If already exists, we know we found a solution, right? Because we know that the complement plus our current number must equal the target. So let's try to write that down and see how that works in practice. So the first thing here that I do is to define a map variable, which is going to be equal to an empty dictionary in Python. And I'm going to be looping over that list once. So for I num enumerate nums. And that's a cool trick in Python where you can use enumerate to get both the index and the number itself. So it saves you some typing. And then for each one of those, I want to be calculating this complement value, which is going to be equal to the target minus the current number that I'm at. And I want to check if this complement already exists in my map, right? So if the complement in map, right? If it already exists, I know I found a solution. And then I can simply say return, now he wants I, and then he wants the index of my complement, right? So map complement, like that. So that's the solution. If I haven't found a complement that's in the map, then I just want to add the current number that I'm in right now to the map and wait for future numbers in my list to check for me, right? So I'm simply going to do map, and here I'm going to add a number, and I'm going to be adding here the index that I'm currently at, because that's going to be useful here for the complement later to reference and return the right index. So that should already work. Let's check it out. And you see here the solution was accepted, and it's a much faster solution. It beats 99% of the submissions, and that's because it runs in O of n complexity. But that's pretty much what I have for today. That's simply the first problem of LeetCode. Every once in a while I'm going to be posting videos like this to go through the solution, and I'll see you next time. See ya.